All right, let's see if my stream is working. Woot, it is, nice. Give it a few seconds for the notification to pop up. There it goes. And my phone probably agrees that it can hear me. Nice. All right. Sweet. All right. Well, welcome to this week's office hours. I will, of course, be going over the heap module that we're now working on. And I guess let's just jump into it. Are there any questions about heap? Or is heap just too easy? Maybe it's too easy. It's definitely going to be more difficult next year. That's for sure. We are currently on an evolution where heap is insecure. Number 4. Okay. Number 4. So I think Jan briefly talked about some of the ideas related to 4, but let's take a look at it. Challenge started. Okay. Then how do I want to do this? I've been thinking about using SSH instead of using the workspace just for some variety in these office hours. You know, now that we're past toddler 1, maybe second half should be the pro SSH rather than this crazy in-browser thing, you know. Go with whatever you prefer, but I think I'll try using SSH and see how that looks, which I've already got set up. Okay, so level 4. Let's go ahead and see what level 4 is telling us. Okay, so an important detail. I'm trying to think if previous levels would have had, I don't know if a previous level yet would have already had more than one allocations, but that is definitely an important detail that right now we're only able to manage one allocation at a time, which is definitely an important detail. And then it says, in this challenge, the flag buffer is allocated 2 times before it's used. So this is a very interesting detail. So if we start by just playing around with some operations to kind of get ourselves thinking about Tcache here. So for instance, maybe we create some allocation. Oops, that was a mistake. This I was trying to specify the allocation index, but in the case of levels where there's only one, you cannot specify it. So that was a bit of an issue. Okay, let's do malloc 32. So we have our allocation, and then let's just go ahead and free it right away and press enter to make sure that that does not collide with my camera. Okay, so we can see right away that in this teaching version of the challenge, it's printing out Tcache to us. And in this case, we're operating in Tcache bin number 1, which is for sizes 25 to 40. It's telling us we have one element in there. And then as hopefully you become increasingly familiar with in these challenges that all revolve around Tcache, that Tcache ultimately is this linked list structure. So we have our head, the head pointer, so the very first kind of starting point of this linked list, and that is listed here. And then we also have this linked list key thing. And this key thing is going to be incredibly relevant in this level. And then so we can see we have this one entry. This is kind of where that's located. Gives us information about this chunk. So we have our previous size, it's 0, not super relevant here. We have our size, hex 31, which has this P flag set on it because the last 3 bits kind of determine these flags. And then we have kind of more relevant this data right here, which is actually, from the perspective of where our allocation starts, this is kind of immediately accessible. Right, this stuff is before, so you'd need, if for some reason you wanted to leak that out or overwrite it, you'd need maybe some crazy stuff to be able to kind of go backwards, but this is where malloc actually gave it to us. So this address here, this 92C0, it's kind of pointing right here. So the first 8 bytes of that is just all zeros. It's a null pointer, which basically, if we think of this as a linked list, we have this object here that's the start, which this is kind of printing out what that memory is. And then the next pointer is null, which basically means, hey, there's not an element after this. There's no next pointer going actually somewhere. And then we have this key object. And this key object is how libc is able to be very efficient about detecting a double free. So we'll see here that, for instance, so we did our malloc 32 and then we freed it, and that's kind of how we got this entry into Tcache. If we go again and just type free, we're going to see that the program crashes. So these kind of specific details change with different versions of libc. So if you were running Ubuntu 18.04, which is on glibc 2 or 229, this double free detected would not happen. It would actually happily free it. Because we're on Ubuntu 20.04 though, and we're using glibc 2.31, there's this updating of the code. The heap is constantly, its code base is constantly evolving with time for various optimizations, for security details, and this is where we're at right now. So if we do this double free operation, we get this double free detected in Tcache, and it just aborts the program. It realizes something is going wrong, and they've decided, hey, this is such a security concern that if someone managed to write a program that actually allowed for this double free, we're declaring, hey, we need to just kill the program because this is super insecure. Similar to like a canary, right? As a mitigation, where if this canary gets overwritten, we don't care. Something really bad's going on. We're killing the program as a security mechanism. Okay, so how is it detecting if there's a double free? So I guess the easiest way to know how it's detecting that it's a double free, and this it turns out that with heap, it's very useful to actually go through and consult with the source code of how malloc and free are actually implemented. So maybe we'll do that real quick. So if I do glibc 231, this B minor, okay, so I already have this in my history. This is the URL we're working off of. So we're in a mirror that's mirroring glibc. We're on version 231 because that is what libc we're using. So if you look around, you could switch to like 2.9, you could go into the future, into 3.4, etc. But we're on 2.3.1. And if we want to understand how does free actually work, right? What is, okay, we are going way too far. If we, moving around my windows, if we look at this double free detected message, maybe we can just control F for that. Double free detected. Okay, so if we look here, this is where it's printing that to us, and we can see there's just one match. So this is definitely where it's triggering that. And if we look backwards, we can see that we're in free, or we're in this int free, which presumably free is somehow calling, or this is an alias for free, or who knows what, but somehow free is making its way to this, which makes sense because we called free and then this message got printed. If we look around here, this block, so this only triggers if this is true. So you can kind of ignore, maybe you, as you read more and more like libc source code, you kind of become familiar with what some of these things are. So this doesn't actually do anything relevant. This glibc unlikely is just suggesting to the compiler and how it's doing its compilation that basically this branch is going to be unlikely to occur. So however the compiler is going to lay out its code, it wants to lay it out in a way where the branch predictor on the CPU for low-level details related to optimization, it's basically saying, hey, this is unlikely, so lay out the code in a way where it's more efficient to assume that this isn't true. Okay, these are low-level optimization details, but that's why that's there. course, these low-level optimization details are there because they're super concerned with the efficiency of malloc, and because they just are generally concerned with efficiency. So anyways, this is unlikely, but we can ignore that. Moral of the story is that it's checking this. If the key, so this key object, which if we go back here, this key object right here, this is what it's referencing. So it's saying E, dereference it, grab the key, where E is our current Tcache entry, which, I mean, if you really wanted to, you could make sure that this all makes sense to you. I'm just telling you that E is this thing. It's pointing right here into this struct. Where the first thing is this next pointer, and then the next thing is this key, and it's referencing the key, and it's checking, hey, does the key equal Tcache? So this would be, is the key what the key should be if this thing was freed? So in this case, this Tcache thing that it's talking about is this value right here. And then the E dereference grab key is this thing. So these two things are equal. And this makes sense. So hold on real quick. I see a message in the chat. The key seems to be within the original user-controlled data, within the actual bounds of the pointer, not outside. Can malloc potentially incorrectly believe that a double free is occurring and crashing correctly? So that is a very interesting point, right? And this, if you look at the source code, it actually directly talks about this. This is exactly what you're saying. So they're saying, hey, this test succeeds on double free. However, we don't 100% trust it, as you're saying. It also matches random payload data at a 1 in 2 to the 64 chance. So it's not an unlikely coincidence before aborting. So they're actually going to take care of this. And if we look at the rest of this code, so as you're saying, it could just happen to have that data, have that key be here. So you could imagine, right, you go and malloc some chunk, and then you write some data here. So we have a valid malloc chunk. We're not about to double free. And then we go and free it. And by chance, this data happens to be there. You don't want this double free detected to happen, because that would not be true. And the way it gets around this is it's checking if this is true. And only if this is true, which in the case of a double free, it would be true, it's going to go through and it's going to walk the entire linked list. So we start by grabbing, this is basically grabbing the head of the linked list. And then it's basically checking the condition is this not a null pointer, right? And then it's going to the next. So this is the classic way in C that you would walk a linked list. And then it checks to say, hey, is temp equal to E, where E is this current thing that we're trying to free? And if it is, that means, okay, no, it is actually true that we've already got this element freed because we've walked our linked list, we found it, and now we can confirm with 100% certainty that this is a double free. And you could think about the implications of why this code is written this way. You don't want to, every time you free, for efficiency reasons, walk the linked list, because this is going to be a bunch of pointer dereferences, which in the grand scheme of things, in terms of how efficient they're going for here, walking this linked list is a slow operation, right? We don't want to do this. So it's unlikely that by chance this is going to happen, but if it does by chance happen, we're going to take the hit and we're going to walk the linked list and confirm it. So that's kind of the idea here of this, what I keep saying, this like efficiency versus security, all being very carefully balanced out. And this is how, like your question was asking, yeah, exactly. But it then double checks that by going through the list, chance or deliberately dereferencing. Exactly, yeah. So this is how it knows to do this. So you could imagine, for instance, that you don't actually need to do this check. We could, in theory, if we wanted to increase security, we could just always walk the linked list. And before we allow the free to succeed, we make sure that it's not already in our linked list. You could imagine an implementation doing that. But for efficiency reasons, we have this key thing, and we use that as a, basically every time you free, don't walk the linked list. But this opens up a security opportunity, or like a security issue, which is that if we can overwrite this dereference grab the key, if we can overwrite this, this check is never going to happen, and we're not going to be able to detect a double free, which means we can't just immediately double free, because when we free it, the key does get set in there. That's kind of how this all functions. But if we go back and we do malloc 0, malloc 32, so malloc a chunk of size 32, and then we free that chunk. So we've got our entry in here, but the program allows us to do a use after free, which I guess in some sense you could think of freeing a freed pointer as a form of use after free, but we've already seen we can't just do that. But what if we can change this key and make it so that this condition is no longer true? So if we scanf and we do, let's say, we'll start with just 4 A's, and we'll see that what we just did is that we overwrote this next pointer. So before it was nil, now we've overwritten it with 4 A's. Well, let's just keep going, right? So if we scanf again, and we do 4, 5, 6, 7, 8 A's, and then 8 B's, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now we've overwritten the next pointer, we've overwritten the key, and assuming we're reading this source code correctly, right, where it's checking if E key, which is this thing, is equal to Tcache. Maybe I should be zoomed in this whole time, but oh well. We'll have to roll with it. If E key, this thing, is equal to Tcache, which I'm just going to tell you is this thing, then we're going to go through walk the linked list and potentially double free out. But this is no longer true, so we're not going to do this check. We have bypassed this block. We're just continuing on in execution. And maybe there's another security mitigation and something is going to catch it, but there's not. And if we free it again now, if we write free, we will see that we got our double free that we so desperately wanted. So now what we have as a structure is we have a count of 2 in here. We have this head pointer pointing still at that C0, and we've got now our address is, so our first thing is this C0, and it's saying, hey, where's the next guy? The next guy's C0 as well, and it points to here. So you could wonder what's going to happen if I call malloc now twice. And what's going to happen is that we're going to get C0, and then we're going to call malloc again, and we're going to get C0 again. And this is a huge issue. You could imagine in some arbitrary-ish program that if you set up the heap in a way where 2 kind of like unrelated contexts within the program suddenly end up with the same memory, and they're not expecting this, and maybe one of those pieces of memory can be user-controlled data, and the other one is containing like function pointers or something. Now the user can overwrite that function pointer, for instance, and then the context of the code that's using it as a function pointer might call it, and suddenly you have arbitrary code execution, for instance. It's very bad if your heap ever hands out the same chunk of memory twice to 2 separate contexts, because the program's normally not written with that in mind, as you would expect. There's another thing, though, which we can see here if we think about this as a linked list, which it is. We have C0, which says that the next pointer is C0, which kind of would imply like an infinite loop, right? Like we have C0 pointing to C0, which means C0 is pointing to C0, 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 which means maybe if we malloc like 10 times, we're just going to keep getting this C0 thing. This was true in glibc 2.29. glibc 2.29, which was Ubuntu 18.04, was a wild place. You could just instantly double free, and you could instantly get every single allocation ever to just keep receiving the same memory. It was a very wild place. But now in 2.3.1, Ubuntu 20.04, this count value is respected. So it's not going to infinitely dole this out, which we will see. So if we do a malloc of 32, we're going to see that we got our C0, and we do a malloc 32 again. We're going to see that Tcache is no longer printing to us as a start. So we got C0, and then we got C0 again, which makes sense, right? We were able to get it twice because we had count 2 and then count 1. But now if we do malloc 32 again, we do not get that C0. So it's not an infinite linked list. But you could, I guess, in theory, if you wanted more entries, do that same trick to get it in there multiple times, as many as you wanted. But yeah, in an older version of libc, you would actually be able to infinitely give this out, which in some ways actually made some attacks more difficult because you'd have to break that chain when you needed to break it because you don't theoretically want everything getting the same memory. You might crash your exploit or whatever. Okay. And the person in chat says, this makes sense now. All right, awesome. Yeah, hopefully you can use this concept, as soon as you have the same thing in memory twice, it's definitely a lot easier to solve this. So there's a question in chat, do some systems that are security critical use custom libcs that opt for all these security checks over performance? So a lot of high profile programs, as far as I'm aware, there are custom heap implementations. So for instance, like Chrome has its own entirely separate heap allocator. The kernel has a separate heap allocator. Yeah, I would say that these big programs, from what I've noticed at least, have basically different security and performance requirements that they often end up writing their own allocators. But that's not necessarily just for security reasons, though they might want a more secure heap implementation. It might just have to do with them having different kind of heap access patterns, like different ways, different structures in which they'll have patterns where they malloc and free in different ways, where this default implementation, it just doesn't make sense for their performance kind of optimization path. They just want their own implementation, basically. And yeah, there definitely might be different security implications as a part of that as well. Yeah, heap exploitation is definitely different, especially compared to a lot of the other modules, in that it is very specific to the heap you're working with. So from what I've seen, I haven't done a whole bunch of the heap challenges in CTF. It's just not something I do that much of. But from what I've seen, the people that do a lot of heap exploitation, they're very frequently reading the source code of the particular allocator because every allocator has different implications. Okay. Yeah. Okay, so are there more questions about the heap challenges? I guess while we're waiting for more questions, what I can do real quick here is demonstrate. What do I want to demo? I want to demo GDB with heap in mind. So let me launch level 5.1. Well, no, let's go with 5.0. It's going to be more relevant on these .1 versions, but it'll be easier to show with a .0. So let's start that. Okay. So we're in level 5 now, and if we do the following, we Emacs GDB init. Okay, so in all of my previous office hours, I have not had this line in here. But now we're going to show off what happens if you start using these fancy GDB plugin or GDB plugins. Yeah, I guess GDB plugins. And in this case, I'm going to show off pwn.debug, but we've also got on the server Jeff installed, which a lot of people like. There's kind of a, I don't know, it's like a Vim Emacs thing. You know, you prefer pwn.debug, you prefer Jeff. You know, it's people have different preferences, but in this case, I will be showing pwn.debug. Okay, so the way that we can activate pwn.debug is literally just adding this to our GDB init to source this file. Okay, so if we switch back over here and we GDB the challenge, we're going to see some fancy colored text that normally doesn't show up in our GDB. And I guess just to really show what happens, I don't think I've shown pwn.debug at all yet. If we start the program, it's a whole different experience than regular GDB. It's in a lot of ways a much nicer experience because it kind of just displays a bunch of things to you that you're often going to be looking at, and now you don't have to enter commands. So for instance, it's going to show you the next several instructions. It's going to show you the stack. It's showing you a backtrace, bunch of registers. You know, it shows you a lot of useful things, and there's all sorts of useful commands built into pwn.debug, as also all sorts of useful commands built into Jeff. Okay. One of these commands, so let me start by running the program and doing some allocations. So if I do malloc 032 to get an allocation and then free 0, we've now got an allocation in Tcache, which in the case of this teaching version of the challenge, it's going to show to us, but it's not going to show that to us in the .1 version. So it might be a little harder to debug, and this is where pwn.debug comes in handy. So if we do, I'm just going to hit Control-C, which is, we're currently inside of a read sys call. It's just going to break on that basically. And if I do heap as a command, we're going to see it print out basically a bunch of allocated and free chunks. So for instance, we have this 2C0 chunk, 2C0 freed entry, and then we can see here this 2B0. So it's off by 16, and the reason it's off by 16 backwards is because this is measuring actually where the chunk itself is, which basically is where that metadata starts. So we can see here that this is printing to us, hey, that there's a freed chunk in Tcache, which might be useful while debugging. There's other commands. We can do Tcache, which is going to basically print out to us all of the head pointers of Tcache, as well as all of those counts. So it's printing out to us kind of this information right here for a particular bin. So we've got 64 total bins in Tcache. And 64, and one of those bins has an entry in it, which makes sense because we freed something, and that entry is located at 2C0, which makes sense because 2Z0, 2C0. So all lines up. Okay, so this is a way to see Tcache. And then another very useful one is Viz Heap Chunks. So if we run this Viz Heap Chunks command, what this is going to do is it's going to be very similar to if we just kind of dumped out a bunch of memory within the heap region, right? We're just kind of linearly going through the heap. But what it's doing is it's actually being super helpful, and it's coloring the unique chunks. And how do I get this to not be where my camera is? Let me think. We'll just print some random stuff. Okay. So we can see it's also over here labeling that data on the right side. So we can see here it's saying, hey, here's for Tcache bins where the size is basically of hex 30-ish. Obviously, that's kind of what if you round up to hex 30. And it's saying, hey, here is the very first entry. This is entry 0 of 1. Maybe that's a little confusing, but this is the first entry within Tcache. And this is all of the data associated with it, this green region. And it's actually starting, maybe slightly confusingly, the very first thing that it's starting at is at, so we know that what was available to us was this 2z0. It's going -8 rather than -16. So this is the prev size, the previous size. This is the size. This is the next pointer. And this is the key. And the reason that this can be useful is that depending on the sort of heap challenge you're working with, the various heap primitives you have access to, it can be common, and I think you'll see this in like the last level even, where you're going to start maybe working from some chunk over here, and you're going to be able to like overflow into another chunk, and it's useful to be able to see kind of directly within this linear region of memory where chunks are relative to each other, so you can watch stuff flow into the metadata of another chunk. This can be a useful command. There's more commands that maybe you'll find useful. If you just Google for pwn.debug and search for the heap commands, this is kind of all of them. Yeah, I guess the other one I didn't show is tcache bins. So we saw tcache, but tcache bins is just another way of visualizing it. Okay, so hopefully that maybe will not be useful for you in terms of being able to debug a heap exploit when you don't have a program that's just printing to you its tcache state. Yeah, you know, most programs don't nicely print this to you. Okay, let's see what's going on in chat. Whole bunch of stuff. Looks like some new people to the chat. All sorts of stuff. Yeah, check out pwn.college. Great stuff. That is what we are currently holding in office hours for. All right, are there any more questions with the heap? Any other levels that people are currently not understanding, or concepts people aren't understanding, or really anything? Anybody? I suppose this is the unfortunate result of shifting the schedule around in a way where we're just one day into the module. People probably haven't had much of a chance to look at it yet. I'm just starting to get into these. So my question is simple, but like, where is the flag? What does the read flag command do? Okay, oops. Does this level does have a read flag. Okay. Let's take a look. So if we, how do we want to show this? Let's see how terrible it's going to look to try and reverse engineer this with obj dump. Maybe we can see what read flag looks like here. Challenge function? Nope. Main. Okay. The issue is that I'm not going to be able to see all the strings. You know what? pwn.debug might print this out for us. Otherwise, we can just switch into IDA. Let's start and disassess. Disassemble name. There we go. No, it's not showing it as strings. So sad. Okay, let's just switch into IDA then. Right. We SCP SH CD projects CDF and college this. Oops. Okay, I see another question. For heap addresses, is it possible to have a sort of wraparound due to an integer overflow? I mean, the immediate answer is yes. It would depend on exactly what you're talking about. And unfortunately, I don't remember or really know all of the House of Blah names, but that sounds very familiar to one of the House of Blah things. And what I'm talking about here is we go to GitHub, how shellfish, how to heap. This is zoomed in. If you look here, or I guess in any glibc version, you kind of look through this stuff, one of these is going to talk about, I think one of these will have that. I think it was House of Force. The question is, does this have House of Force? House of Force. It does. Maybe this no longer works in 231. 227 definitely has it. We look at 227. You can see this is like laid out per libc version because this stuff changes. House of Force. Right. Allocate. The size of the wilderness is now gigantic. Without calling with an integer overflow. Sounds like what you're saying is reasonable. Yeah, so if you look through this, this is a way of kind of understanding more specifically what that would look like. So this will have various allocations it'll do and maybe modifications to memory. It's going to kind of walk you through the general structure of the attack from the perspective of writing the source code and the exploit kind of interweave together. And yeah, that'll kind of talk through what that actually is. But yeah, there's all sorts of heap attacks. Is the font only for me? Yeah, so I didn't zoom in on this. Hold on. IDA 64. How do I do this? IDA. New. So many files. College heap level 5. Okay. Took forever, but we are now loading this into IDA. Okay, hopefully this is readable enough. If we decompile this, and unfortunately IDA doesn't do a very good job at decompiling these switch statements in a while loop, but it should hopefully be good enough. So if we look for what the question was basically what does read flag do? If we do this stir compare with read flag, so if it'll break if it's not this, otherwise it'll continue. And what it's going to do is it is going to malloc one time from 0 to less than or equal to 0, so that means one time. It will malloc a buffer of this size, and then it's going to open the flag, and it is going to read it into the result of malloc, so basically whatever we just malloced, plus 16. So it's not reading it straight into the beginning of malloc, it's reading it into an offset of 16 from that malloc, which is important to know. And then there's also kind of the complementary function puts flag, which does, it's checking if this thing, so we're calling this size 4, maybe we should call this flag chunk. If this thing exists, oh, okay, so it's what it's doing here. So we read into flag chunk plus 16. And then here in this case, it's looking at the very first 8 bytes of flag chunk and basically seeing, hey, is this non-zero? And if it happens to be non-zero, then it's going to output the flag. Otherwise, it's not going to output the flag. So kind of the trick of this level, I think I'm looking at level 5, is that we have the ability to read the flag into memory, but we don't have the ability to immediately use this puts flag because we're not going to pass this check. So somehow we have to control the very first 8 bytes of this allocation and make it be non-zero. So you have to think about kind of what your primitives are in terms of being able to overwrite the first 8 bytes of this. So there's a question, why do you prefer IDA instead of Ghidra? I don't really have a huge preference one way or the other. I guess I'm just more familiar with IDA. Okay. So hopefully it makes sense that this is kind of where the challenge comes in, that somehow we have to make the first 8 bytes be non-zero. And we don't have like I guess we have scanf, but you'd have to maybe think about how you can get this. Actually, do we have scanf in level 5? Level 5. Malloc free puts read flag puts flag. We do not have scanf. So if we had scanf, you could imagine using the tricks that we were using before to kind of, you do a use after free. So basically you'd make it so that this read flag gets a chunk that you currently have a reference to for these other things, but we don't have the ability to scanf into it. If we had scanf, it probably makes more sense how you would do this. But without scanf, you have to think about what are your write primitives. So something here is going to let you write to memory. Yeah. So think about it from that perspective. We just need to make those first 8 bytes be non-zero. Think about the implications of malloc and free and tcache and how all of this linked list stuff works in terms of what allows you to start writing to memory. Because even though we don't have a scanf, we still have stuff that's going to write to memory to kind of maintain that whole linked list structure. And this is really what all of these challenges are about. So all of these challenges are all about deeply understanding the linked list structure of Tcache and really getting comfortable with using these functions to kind of abuse that linked list. Okay, so read flag mallocs and puts a flag inside of it. We can malloc ourselves as well. So we exploit to get a malloc. We made to have a flag in it so we can puts it. So we can't puts it. So I guess we can kind of walk through part of some thinking here. So if we, for instance, I guess we need to know what is the size of this malloc with the flag buffer is on. Read flag decimal 648. So if we malloc 0648 and then we free 0, so we now have this sitting in Tcache, this 2C0. And now if we do read flag, we're going to see it got that 2C0, which means our allocation 0 we can do arbitrary use after freeze with right now. So we have something pointing at the same thing. But the issue is, right, if we do puts 0, it's not going to print anything to us because it didn't read the flag into the beginning of this. It did it 16 bytes later. So you have to think about how you can modify that first 8 bytes, because if we can make the first 8 bytes be something other than 0, we get the flag. Isn't Tcache volatile memory? It's thread local. So the Tcache, the T stands for thread, or maybe even thread local, or it's in thread local storage. But I guess that's not actually true for the main thread. The main thread stores it in the main heap, and then if we started creating additional threads, those would be stored in thread local storage. I don't know if I would call thread local storage volatile though. I don't know if that fits into the definition. My understanding of volatile memory would just be memory that can suddenly be changed by some external thing. And I don't think it meets that definition. Did that earlier technique make malloc return a nearly arbitrary pointer? Yes, so probably what you're talking about here with kind of all of the things we have access to, oh, but we don't have access to scanf in this level. We quickly switch to probably, oh, we can go with 4. I think 4 has what we need. If we run 4, if we do malloc 32 bytes free, okay, so now we have that sitting in Tcache. And if we do scan, well, hold on. The issue is that we don't have the immediate ability to, we can't modify the head is the issue. We can only modify this, which means we can modify the next thing, but our count is 1. But we can use the trick that we were talking about before to kind of get this thing in here twice as just to demonstrate this. So if we scan F onto here and we do 8 A's, 8 B's. Okay, so we overwrote the key, and now if we do a free again, and the reason I'm doing this is just to get count up to 2. Now if we overwrite this, so if we do scanf again, and we do A, B, C, D, E, F, G, H, whatever, we can see some crazy stuff is happening now. Now we've just overwritten this next pointer, And you can see that our little nice printer thing is getting confused because this is not allocated memory. So in the case of non-allocated memory, it just starts saying, I have no idea what's here. And if we do, now if we do malloc once, size 32, the very first thing we get is that head pointer, which makes sense. So we got this. And then now we can see that our new head pointer is what we had overwritten with, which means now we can do malloc again of 32. And unfortunately, we crashed the program here, but you could imagine doing things a little bit more carefully. But what was about to happen is we would, in theory, be getting this back. The reason that we're crashing is that we're going to this address and we're writing memory here. Basically, we're erasing the key, I believe. Actually, I think we're nulling out the first 16 bytes entirely. I think we just entirely null out the first 16 bytes, but we can't do that because this isn't mapped memory. Yeah. But yes, these primitives can get very powerful. We can get arbitrary allocations to places, which means with puts and scanf, that means suddenly now we have arbitrary writes and arbitrary reads. So there's a question in chat, what is the crash? So the issue is that it doesn't just return to you what is at this head pointer. It doesn't just immediately return this to you. It also goes and writes to the first 16 bytes of memory null bytes. So it can't write 16 null bytes here. That's a seg fault. But if we had done an allocated region of memory, we would be able to write those 16 null bytes and we would have successfully gotten that. It's just as part of Tcache, when you call malloc on a size where there's Tcache bins available, the operation is it's going to get ready to return the value at head to you, and then it's going to null out the 16 bytes. And if count is, if there's more entries that are going to be available, it's also going to read the first 8 bytes to determine the forward pointer and grab that and shove that into the head region as well. Which is kind of how this worked up above, right? We got this value, we dereferenced it, we saw that this is next, and that's how that ended up there. Okay. Oh, okay, that was a different answer. I see. Okay, let's see here. Yeah, I mean, Tcache definitely lives in RAM. Yeah. Just to check if I'm on the right track, we find a way to overwrite some Tcache next attribute to a stack address, and then malloc that appropriate chunk size twice, we will be able to write to the stack by using the malloc pointer. Yes, exactly. I'm trying to overwrite a small piece of the canary with the letter A to get a stack smashing detected, but it's just giving me seg faults. Is there any recommended literature alongside the website problems? So if we go to pwn.college and we look at this module, there is further reading, I guess, which involves this and this. So malloc internals is just basically going to go through and very meticulously document the internals of malloc and how it all works and all the terminology associated with it. It'll be very in-depth with all of this information. And then how to heap talks about all sorts of various exploitation primitives. And I believe all of these modules have some amount of like reading associated with it if you're asking more broadly. Maybe sandboxing, read this. Oh, I guess that's specific. Some of these things have extra things, but they also all have lecture videos. If you're asking broadly, we have videos discussing all of this and slides accompanying it, etc. So it's not just the challenges, there's all sorts of lecture material as well. Okay. So by allocating, okay. Do you know a good resource for the Tcache stuff? Well, my best answer to that would be pwn.college's baby heap challenges, of course. That is a good resource for Tcache stuff. Beyond that, I mean, I would also make sure you watch all these videos. Yeah. The hope is that these challenges, build up your understanding of how Tcache works very slowly and progressively. And then you can always refer to the lecture videos, ask questions in the Discord, etc. But there's probably other things as well. So for instance, I'm thinking of CTF Wiki is a thing that exists. Don't know. Issue, is there English? Yes. Heap. Tcache. Well, this is not translated into English. I think there's another CTF Wiki. CTF Wiki English. Yeah. Does this have it? Tcache heap. Sweet. So this might also be another useful resource that is just going to talk about Tcache and how it functions. It's a linked list ultimately, right? And hopefully the teaching output will make it very clear how it's operating when you call malloc and freeze and kind of mess around with that stuff. But if you'd rather read some stuff, this could also be useful. All sorts of stuff. Okay. Should we be able to start from module 1 to be able to solve later modules? So we do currently with pwn.college assume some knowledge. So we're kind of already assuming that you're familiar with writing C, ideally a bit of assembly. You kind of have some concept for like system calls and the kind of basic operating system course. And kind of some understanding of kind of some Linuxy things. So yeah, it's not, I probably wouldn't say it's currently approachable if you have absolutely zero background in any of this stuff, but give it a try and see how it goes. And someone's saying embryo ASM is great for learning assembly. Yeah, so that this requirement probably is a little less required. I would say it would probably be good if you have some experience just kind of like writing some C programs. The hope is that eventually we can make pwn.college approachable to someone with literally zero background in even programming, but we're not quite there yet. Are these heap exploitation techniques exploitable with the actual malloc implementation, or is it only for the latest version of it? So it changes with every version of libc. So the current thing that we are targeting with these challenges is glibc 2.31, which is what you're going to be using if you're using Ubuntu 2004. That's the default libc with that version of Ubuntu 2004. Next year, when it's Ubuntu 2204 as the kind of latest long-term release, I believe it's going to be on libc 2.34, I think. Not 100% sure on that. And things are going to change like crazy. If you're interested, you can Google libc safe linking this kind of stuff. There's a whole new crazy thing that's getting built into how this metadata is stored that is going to fundamentally break these challenges. It's kind of, you could imagine before there were canaries and then suddenly there's canaries, right? Like that sort of thing. It's a huge protection mechanism. It does have bypasses associated with it, but it's a harder problem, which we will address next year, I guess. Yeah, it's definitely interesting reading through. If you're interested on kind of the more defense side of security, it's definitely interesting reading through kind of these cutting edge security mechanisms that are being implemented to help prevent a lot of attacks. Okay. Are there any more questions? I thought offense was the best. Yeah, I mean, the turns out that in hacking, you know, offense and defense kind of go hand in hand. You can't really do defense if you don't understand the offense, and vice versa. You can't do offense if you don't understand the defense. They kind of go hand in hand with each other. Yeah, you saw an XOR symbol and get PTSD from AES. Yeah, it's a very, I don't know, it's a very mathematical sort of security mechanism. I mean, not really, it's just an XOR, but I think it's an XOR with some bit shifting. It's very, very scary looking though. Math is fun. Could you send the link of this site? Yeah, if you just Google for libc malloc safe linking, the new technique is called safe linking, but I sent that. Oh, and I guess someone else sent pwn.college if that's what you meant, but I don't think that's what you meant. How do you keep integrity for Tcache for investigation purposes? Integrity for Tcache for, I don't know what that means. Keep integrity. Like you would a drive? Drive. A drive? Would you keep integrity for, to prove? Oh, to prove the information is the same. I think I maybe know what you're saying. Like as a security mechanism, to prove the information is the same as it was when you started. So you could, I guess, have, maybe I kind of understand what you're asking. What you could do, so if we look at this, so all of this metadata is being stored. Maybe it makes more sense if I look at like this. So all of this metadata right now, so this is a freed pointer, and we have this metadata being stored at where the pointer was pointing to and this other metadata that's before that pointer. You could imagine instead of storing all of this metadata intertwined with the data itself, which means stuff can be corrupted in the case of a use after free or whatever, you could imagine storing this metadata entirely separate from this. Like don't intertwine metadata with potentially user controllable data is kind of a big thing. If I had to guess, the reason that they're intertwining this is for optimization reasons. Like we have this freed memory, you might as well store some metadata in there because no one in theory should be caring about it. So we'll just shove metadata in there. But it does have these security implications that if we have a use after free, we can start potentially controlling this metadata. But yeah, it's all a security performance trade-off. I'm sure there's some libc developers out there that would say just don't have a use after free. And then this isn't an issue. Just don't have security issues and then it's not an issue. There's all sorts of considerations. I mean, it's not just that simple, obviously. Performance, it obviously matters, right? If you're doing potentially millions of mallocs on some arbitrary program, it would be pretty nice if malloc was running pretty fast. So it's a difficult balance that is especially seems to come up in Heap, of balancing security with performance. It's a very, very tricky thing. and just have no bugs. All right, are there any more questions before I start wrapping up this office hours? Maybe I'll have another office hours on Monday or something, we'll see, where people have had more of a chance to approach the challenges. Not 100% committing to that, but maybe it will be useful. Okay. Any final questions? Not seeing him. All right. Well, thank you for joining me for this office hours. As always, feel free to ask more questions on the Discord, and we'll have our extended Q&A tomorrow with Jan. I guess for the new people, that happens. What time is it now? It's like 5 Arizona time. So in 23 and a half hours, I guess, 4:30 Arizona time, we'll have the extended Q&A with Jan. All right, thank you all for watching.